Okay, so next subtopic, BJT as an amplifier. So this is going to be our input signal, V in, a sinusoidal signal, and we are going to get the output between these two. This is going to be our output, V naught. So we are going to use this transistor to make an amplifier. This is the collector resistor, base resistor, and our emitter resistor. In addition to the previous circuit that we were discussing, here we have some capacitors. Let's name them as C1, C2, and C3. First, I'll explain how this works. So we know that a transistor can work as an amplifier in active mode. That is very important. Only in active mode, okay? Not in saturation or cutoff. Only in active mode. This works as an amplifier. So in active mode, IC is equal beta times IB. Full stop, where IC is very much greater than IB. By sending a small current, you can obtain a large current. So therefore the current, input current IB can be amplified as IC. By sending an IB current, we can get it amplified as IC current. So this is known as current amplification. I have drawn the diagram. Okay. When a small sine AC source, sine AC source, and a small sine AC source is connected to the input, is connected to the input, to the input circuit. IB and IC, IB and IC swings or fluctuates, or fluctuates as shown, as shown. So when we have a sine voltage supply, then the IB current with time is going to swing. IB current is going to swing with time. But you might have an idea that AC current means it has to go in the positive side and the negative side, right? But here we have both of them in the positive side. You might have a problem with that. So can you remember when I was biasing, I'll go back to biasing. So when I was biasing, did the voltage go below this point? No, right? Just because I applied a wave like this, just because I applied a wave like this, the voltage difference between these two didn't go below zero for the current to flow in this direction. The current didn't flow in the opposite direction. Current was always flowing in the same direction. Okay, therefore, IB current won't be going below this time axis. So if we look at the IC current, now we have a direct proportional relationship, right? IB is equal beta times IB. IC is equal beta times IB. So its value will get amplified, but the time and all remains the same. So the only difference between IB and IC is its magnitude. Both of them are in the same phase. So here, although they look the same, this has to be beta times IB. Beta times IB. Okay. So this maximum value here and here are not the same. Only the shape is same. Okay. You cannot compare the size according to this graph because we cannot draw this graph 100 times greater than this. For now, we are only talking about the shape. Now let's look at the voltage variation at the output. Before introducing the AC signal, the output voltage, the output voltage VCE varies with VBE as follows. So what we are going to do is we are going to check how VCE is going to vary with VBE. So what is VBE? VBE is not a AC signal. It is not the AC voltage because we didn't introduce the AC signal yet. This is before introducing the AC signal. Okay. Therefore, it is a DC signal. So to understand this, we will have to go back to to an example question we did. So here, let's look at this example. In this example, what can you tell about this voltage? This voltage is constant, okay? This voltage is fixed. It is not going to change. Now, if IB increase, if IB increase, then IC will increase, okay? That means this IC current will increase. If IC increase, this voltage VC has to decrease. Why is that? We need a potential difference. We need a potential difference. So if I write 10 minus VC is equal IC into RC. If IC increase, this term will increase. If this term increases, the voltage potential drop also has to increase, right? But this is a constant value. Therefore, VC has to decrease. Did you get it? So if IC is increasing, VCE decreases. Is that idea clear? If IC increase, VCE decreases. Sarah, okay. So if we plot the VCE versus VBE, when VBE is in the cut-off region, then there is no change in VCE because C won't change. If IC is equal 0, VC will be, there will be a constant value, okay? So it remains the same. But when IC starts to increase, when VBE is in the active region, okay? It is in the active region, then IC starts to increase, VC starts to decrease. Therefore, VCE decreases. And after saturation, once saturation is reached, even when VB increase, IC remains constant. During that, VC will remain constant. So it remains constant. Is that idea clear? So this region in VCE versus VB graph, this region is going to be our cut-off region. And this region is going to be our saturation region. And this is the active region. Okay, clear up to this? Sarah and Saja, clear. So we can tell that VBE increase, IB increase, IC increase, VCE decrease. So therefore, VBE increase, VCE decrease in active mode. Okay, note that one also. So now let's introduce the signal, the AC signal. Okay. And before that, we have to mention that from this graph, from this graph, we can get an idea. That is, when input signal increase, the output signal decreases. From above, it is clear, that output signal decrease, when input signal, increase, in uh, active mode, in active mode. So now we can get an idea about how uh, it will fluctuate when an AC signal is given. Okay, when we introduce an AC signal, by introducing the AC signal, VBE and VCE swing at their values, as shown. So our input signal, we give it to VBE, right? Now VBE versus time. So if you can remember, VBE is also not going to be negative, okay? Now let's say this is varying like this. We have a fluctuation as shown. Then our VCE versus time is going to be as follows. When VBE increase, VCE decrease. When VBE decrease, VCE increase. So this is the input signal we gave. This is going to be the input signal that we supplied, delta VBE, and this is the output signal we obtained between these two. Delta VCE. Delta VCE is greater than delta VBE, and also the output signal, the output is 180-degree out of phase. Clear with these two graphs. So that's the idea. That's the idea of amplification. So when we give a signal, that signal gets amplified here. If we check the input and the output is 180-degree out of phase. Okay. Let's write a note. Note number one. Note number one. Load line. Can you remember this graph that we drew between IC and VCE? We drew a graph between IC and VCE, keeping IB constant, just like this. When IB is 0, this is when IB is equal to 0, and in this direction, IB increases. So we didn't get a proper idea about this graph. Now let's understand what this graph actually says. So here, don't draw what I drawn up, only draw this graph. Now I have my transistor. I provide a signal just like this, a sinusoidal signal. Now this signal, now we have plus VCC. So this signal is having a low value, right? It starts with a low value. When the low value is 0, IB current is not 0 because it is already biased. Because it is already biased. No, let's start with input 0. Now I have a curve like this, and in this curve, I'll say the input is 0. Okay, I supply 0 voltage, and VCC is 10. VCC is 10 volt. So if this is 0 volts, what can you tell about IB? IB is equal to 0. IB is equal to 0. If IB is equal to 0, IC is equal to 0. If IC is 0, is there a potential difference between these 2 points? There is no potential difference. Therefore, this voltage is going to be 10. Okay, now I'll increase this voltage to 2. For this voltage 2, there will be an IB current. There is an IB current. For that IB current, we have a IC current. If there is an IC current, this voltage will decrease. Let's say it decrease to 8 volt. Okay, now I'll go to this graph. In this graph, when IB current was 0, there is this graph, when IB current was 0, VCE was 10 volt. So it is somewhere here. Okay, and when this is 2 volt, there is an IB current. Therefore, not this line. Now I have to check this or this line. Okay, can you remember these graphs were drawn for different IB values? Let's say for 10, 20, 30, and so on. We drew these graphs for different IB values. So IB has increased. Okay, IB has increased. From this graph, IC also has increased. At the same time, VCE has decreased. Therefore, this point, now just think this as the working point. This point will move up, at the same time it will move behind. Okay, if I further increase, it will move up and it will move behind. Moves up and moves behind. So if I connect all these working points together, If I connect all these working points together, I will get a straight line. So that line we call as the load line. So the transistor will be working in this line. Always the output will be somewhere in this line. Is that idea clear? Both of you okay, right, with that? So here, I also mentioned that in this one also we can show the regions. This one was clear. This is our cut off region, okay? And in between, look, in between, I get a value, for IC, right? IB increase, IC, we have a value. IB increase and IC, we have a value. So here we get values for IC. That means when I give a voltage, there will be a corresponding output. So this region is the active region. Okay. Now, how this one becomes the saturation region? How this becomes the saturation region? Now look, when we are working, when we are increasing the voltage little by little, I mean, when I'm increasing the input voltage little by little, the working point is moving up and going behind, moving up and going behind, and it goes behind this point where we are not able to get a IC value. So here, whatever value I apply for voltage, I am not getting a IC value. So that will be my saturation region, right? Is that clear? How we uh, got the idea of each region. This is the cutoff, this is the active, and this is the saturation. Okay. Now, in this, we have a point. First, draw this graph. So, if I write the equation, VCC is equal ICRC plus VCE plus IERE. What is this? It's like this. If you have a transistor, now this is VCC, this is RC, and here you have potential drop VCE, and this is RE, and this is earthed. So VCC is equal ICRC plus VCE plus IERE. Here I'll get IC as the subject. I'll get IC as the subject. So I have IC RC is equal minus VCE plus VCC plus IERE. And IC is equal minus 1 over RC VCE plus VCC plus IERE over RC. So this is the equation for the load line. Okay, equation of load line. Can you remember here before introducing the AC signal, we got an idea about the variation for DC voltage This is also similar. Here, before introducing the AC signal, I am getting the idea of a DC current. Okay, for a DC IC current, how it will vary with VCE. Hope the idea is clear. Once you have copied, let me know. Below this, write down load line. Load line is a straight line. Is a straight line used to locate used to locate the optimum biasing optimum biasing or operating point or operating point of a nonlinear device of a nonlinear device. Usually BJT or FET. BJT or FET. So what is this operating point? Operating point means here, now we will talk about the Q point. In this diagram, mark Q point. Our purpose is to find this Q point. Note number 2, to understand Q point, let's take an example. We try to keep now let's say we applied a voltage of V So we are giving a signal of V. Now what we will try to do is we will try to place this voltage at VCC by 2. Can you remember bias? Okay, biasing, bias voltage. When we supply the bias voltage, we will try to keep this voltage at VCC by 2. So what is the purpose of that? The purpose of that is now, don't write what I am writing, only this diagram. Don't draw what I am drawing now. Now let's say our output voltage, so this is my transistor. In my transistor, the output voltage is supply voltage. My supply voltage is 5 volts, and I have not biased it. I have not biased this. If I did not bias, then my voltage will be at, it will be at 5 volts. If I have not biased this will be at 5 volt. Why is that? When this voltage is 0, IB current is 0. IB current is 0. When IB current is 0, IC current is 0. If IC current is 0, there is no potential difference. So, no bias means this voltage will be at 5. Okay. Now let's say I give a signal like this. In this signal, this part has a positive signal. So, VBE is increasing, therefore VC will decrease. VC will decrease. But